So we have two exam questions here. So in both cases, we want to write them in the form a to the power of m, a to the power of n, where these are rational numbers. Rational numbers is just a fancy word for elements of just fractions. Okay, so we'll take our time here. One thing we can do is see this as top, top, bottom, bottom, in which case you could see this as a cubed divided by a to the minus 1 times b to the minus 2 divided by b squared. Now with the negative powers here, I wouldn't, you can kind of be clever about it rather than using rules, say, but I think here really you should use the rules. Okay, so I'd say division of like powers, you subtract the powers, and you want to be very careful here. People that make a lot of mistakes here. So it's a to the power of 3 minus 1 times b to the power of minus 2, and people are often making little mistakes here. So 3 minus 1 is 3 plus 1, which is 4, and minus 2 minus 4. And then what you want to do is use the fact that the power of a product, where's it gone? So that's what we have here. So two numbers to a power. I haven't left much space for myself here. You apply the power to both of them. Now, so you're going to have a to the power of 4 all to the power of minus 1, and b to the power of minus 4 all to the power of minus 1, and then use the fact that repeated powers means multiply the powers. So 4 by minus 1 is minus 4, minus 4 times minus 1 is plus 4. There you go. Another question, simplify this. So we'll take our time here and I'll use the rules because it's a little bit harder to be clever about it, and remember that the square root means the power of a half. So this thing is equal to all to the power of a half. I'm going to write the a as a to the power of 1, and then on the bottom, so here this doesn't make as much sense because I don't really know what I can talk about division if I want, but ultimately, like if it's a squared a cubed, I say 8 to 5, no thinking involved. But here there's too much thinking, so I'll just use the rules that I know the definitions are consistent with. Multiplying together like powers, you add the powers. So a to the power of 2 plus minus 3. So we have a to the power of 1, and 2 plus minus 3, otherwise known as 2 minus 3, is minus 1. And now being careful here. Now you could actually, if you wanted, you could go at this now. I think it's a bit better to go another line. So division of like powers, you subtract the powers. So again, being careful, 1 minus minus 1, all to the power of a half, and 1 minus minus 1 is 1 plus 1 is 8 to the power of 2. And maybe here I could be a bit clever and recognize half is square root of a squared is a. But let's be a bit denser and just use the rules. Repeated powers, you multiply the powers, and then 2 by a half is 1. Now, we'd be clever, if it asked us to write it in the form a to the power of p, we'd be done, but it just asks us to simplify it, so we get finally a. Right. More questions. So an exponential equation of a particular form, so this will be, I'm going to write a nice exponential equation because we're going to have nastier ones a bit later, is an equation of the form b to the power of x is equal to b to the power of y. And we're going to have a little theorem here that if the base is positive, not 1, yeah, and if you've got two like powers are equal, then the powers have to be equal as well. This isn't always the case that you have something like this. So for example, non-theorem, for example, would be if you take if x squared is equal to y squared, then x is equal to y. That's not true. It's a non-theorem because, for example, minus 2 squared is equal to 2 squared. They're both equal to 4. Minus 2 by minus 2 is 4, and 2 by 2 is 4. They're equal, but it's not the case that 2 is equal to minus 2. This is about invertibility and about being things one-to-one. But here, yeah. So we could actually, I'm going to come back on this page in a second. I'll do it now. So the story actually is that for b bigger than 0, the b to the power function is 1 to 1. And if it's 1 to 1, what does that mean? Well, let's see. And we're going to show, we're going to draw a picture on the next page kind of saying why it's 1 to 1. I think the b to the power goes from r to r plus. And so what we have here is we have two different inputs, x and y, having the same output, b to the x equal to b to the y. But the story is because b to the power is 1 to 1, this cannot happen. And so in fact, these two must be equal. You can't have two different things hitting the same thing. So because b to the power is 1 to 1, if the two outputs are equal, the two inputs have to actually be equal, okay? Which doesn't happen with squaring, for example, because you can have two different things. It isn't, squaring is not 1 to 1. So let's write down something here. So the squaring function is not 1 to 1 on real numbers. Okay. So we've kind of, now I've just said b to the power is 1 to 1. Let's kind of explain it a bit. So all functions of this form are increasing for b greater than 1. If b is between 0 and 1, you can basically show that it's decreasing. So now you need a bit more to show that it's increasing, but trust me, it is. So by the horizontal line test, this function is now called p. P is 1 to 1, and now you could say it's onto, actually there's probably two ways to argue from here. So if it's 1 to 1, then what we argued on the previous page holds. Alternatively, you could actually go further and say it's onto the positive real numbers. So like if you draw any line for positive real numbers, it'll hit it. Therefore p inverse exists, which we'll be talking about a bit later. And so what you could do then is, if you b to the x equal to b to the y, you could apply the inverse function to both sides, which would be p inverse, and you get x equal to y. Because remember, if you're 1 to 1 and onto, you're bijective and you're invertible. So that's one way of kind of showing this. So if b to the x equal to b to y, then in fact x equal to y. Note that for large negative values of x, like x to the minus 10, b to the x is approximately 0. So this goes to 0 in this direction. So I'll write b to the minus n. N there is supposed to be some big number. It's approximately 0. Why is that the case? Remember, negative powers are division. And so say b to the power minus 10 is 1 over b to the 10. And if b is like even 2, that's 1 divided by a very, very big number. And dividing by a big number, you get a small number. This is 1 to 1, and so invertible on its range. And in fact, well, if you take b to the x, depends on this function here. So if you take it as r to r, it's not onto, because it doesn't hit any negative things. So it's only invertible on its range. But if you consider it as r to r plus, then it is in fact onto. It hits all the positive real numbers. If b less than 1, it's decreasing. If b is equal to 1, it doesn't work because you have a constant function which is not 1 to 1. Everything is sent to 1. All right. So therefore, if you can write an exponential equation in the form, say, b of f of x, so that I just mean some form in x, b to the power g of x, you can say that these are equal. Now it'd be nice, and actually by the end of this you'll be saying, okay, via its inverse. So the p, so that's called p of x equal to b to the power of x, which we'll call b to the power of x. So we can get rid of this b to the power using b to the power inverse. And you can say that these two are equal. We'll be talking about this function quite soon. So there's exercises here. Now you can check. So it says, while the calculator can give you the answer to some of the questions, it cannot help you with all of them. So what I want you to do is actually struggle without the calculator so you can understand the concepts. And later on, you'll be able to use the calculator or your head, and certainly your head when the calculator is not an option. So I'll make some comments on these questions. So you're going to use these definitions, page 165. See, the thing is, like, we could ask you for a to the power minus half. Your calculator's not good to you. These ones, so this just means a fraction. And you will also need, so this is definition. This one's a bit tricky. So you can use a definition or definition plus fact. And by fact, I mean this stuff. This one is probably definition and a little bit extra. This one is definition. This one is definition. Right, these is powers of 2. So my hint here is write 8 as 2 to the power of 3 and use the axioms, and write 2, 5, 6 as 2 to the power of something and use the axioms. Okay, so here these are, this uses, I think, definitions. Can't do a calculator. This is definitions. Yeah. This is just simplified. So yeah, p is a natural number, just means that p is a fraction. Simplify this out. The answer I will have up next week, I presume. Yeah. Now this is definitely not to be done with calculator. So this is just to test your understanding and feeling for these powers. So here, if you've started looking at logs, use them. Do use them. So that's if you watched all the log lectures, use the logs here. These are all a mixture of axioms. Page 165. So the first one is an axiom, as the second, as the third, the fourth is a definition, etc. Okay, these are probably additional exercises. So I'm not as concerned. Now they're not harder actually, they're just additional. So true or false without a calculator. Simplify, give the answer next week. Simplify answers next week, I suppose. Simplify these ones using what I'm calling the facts. And another question for you. Okay, so that is, I'll probably put this part of the thing highlighted in the exercise bit. Now I got a just extra bit here. There's a good few pages just talking about units of data, but it's not examinable. It's just some nice stuff for you here. Okay, now let's talk about logs. Right, fix a base bigger than 1. So this b is called a base, and usually it's base 2. So this is what you know about binary. Base 2. And consider the function p as b to the power. So you're thinking for this one. So you put in a number, you put out 2 to the power of that. So minus 3, 2 to the minus 3, minus 2, 2 to the minus 2, minus 1. 2 to the minus 1 means divided by 2, which is the same as a half. And then 2 to the 0, anything to the power of 0 is 1, etc. So we plotted some of these points. Remember, input, output. So say this would be input 0, output 1, input 1, output 2, input minus 1, output half, etc. Okay, we plot this. So the graph of this. I suppose it's just an interesting question. How do you show that this function is increasing? There's other stuff in the background. You're just going to have to take my word for it. So this is never 0, and it's strictly increasing. And a graph is all the points of the form input output. By the horizontal line test, if you draw anything, it's 1 to 1, and it's onto the positive numbers, and therefore it's bijective, and therefore it's inverse. The inverse of 2 to the power exists. Okay, so this suggests we could define a function going the opposite direction, the inverse. So because remember, so like for example, if you have squaring, now we'll have a small domain and codomain here for squaring. So let's take 0, 1, 2, and so this is a set x, and then a set y, 0, 1, 4, and we could define a function which I'm going to call square from x to y. And we also could, because this is 1 to 1 and onto, its inverse exists, we can define the function going the opposite direction. So 4 back to 2, 1 back to 1, and this one. So the inverse of the square function here, let's call this squaring on x, going backwards is the square root, and let's call it the square root on y. It just goes backwards. And in terms of the graph, so well, let's write down the ordered pairs for square. So square function is 0 is sent to 0, 1 is sent to 1, and 2 is sent to 4. Squaring on x. And then square rooting on y, which I have in green. How do you find it? You just turn the ordered pairs around. So 0 sent to 0, 1 sent back to 1. I probably shouldn't have used 0 and 1. And 4 is sent back to 2. So if you think about this kind of dynamic thing where, say, for the 2 to the power function, you've got 1 is sent to 2, 1 sent to 2. You can define a function going the other direction, the inverse of 2 to the power, where you go 2 back to 1. So that going the other direction is the 2 to the power inverse. Okay, the inverse of 2 to the power. So I'm going to probably, so this other function we call L of x, it'll only take positive numbers. So this inverse, say, now let's work with let's work with b to the power because it's a general thing. No, let's work with 2 to the power, excuse me. So 2 to the power inverse goes in the opposite direction. So if the power goes from, I think we need to go to plus, so it'll go from positive numbers back to real numbers, positive reals back to reals, and we're going to define log x as the inverse of this. Okay, so we're going to say log of x. Now here, without the base, often this is, now the base is this number here, so you can change this number and you get different logs. But in computing, usually log means base 2. But there's other possibilities. So log base b is the inverse of this. Okay. So what else we write down? And log base b is the inverse of b to the power. Okay. Right. So let b be bigger than 1 and p of x be b to the power function. The logarithm base b is a function going, now p here goes from real numbers to positive reals, so its inverse goes back the other way. That is the inverse of p of x. And then one important thing is that when you apply a function and its inverse, same as doing nothing, which is the identity. So what this means would be that log base b after p is the same as doing nothing to a real number. We'll explain this down below. And if you do log base b first and then do p, well, that would be the identity as well, but it would actually be the identity on positive real numbers, so let's get rid of that. Okay. That should be too abstract. So the I is where you, whatever the input is, you have the same output. Okay, so let's kind of do this a bit easier. So we'll write it in now we'll have some examples to explain it as well. So let's write down some things. So let's take a number, let's take an easier number, let's say number 3. So if you apply 2 to the power of 3, now it could be b, it could be 5 power 3 here, let's take, say b is equal to 2. So if you do 2 to the power of 3, so that's you've started with 3 and you've done 2 to the power, log base 2 is the inverse of that. So it should get you back to where you started. So that's the same as up here. Say take 2, square it, square root, you end up back where you started. Start with 3, do 2 to the power, and then do log base 2, you end up back where you started. And if you start with the number 3, do the log of it, say log base 2, and then do 2 to the power of it, the 2 to the power, you end up back where you started at 3. So they're inverses of each other. See, the log base 2 gets rid of the 2 to the power. And the 2 to the power gets rid of the log base 2. Okay, it's probably one thing I should probably write down. Something you might see somewhere is that log base 2 is often also written as LG. Okay. Right, so it should be complicated. That's okay. It's a bit hard. We've used a lot of language from the previous chapter, but ultimately we're saying that logs are the inverse of what are called exponential functions, these b to the power functions. I think we're going to get a bit more understanding over here. So yeah, so this is what's written down here. And what you can do, you definitely want to be using this a lot. So this is, I'll probably explain this in terms of this. Now this is base A rather than base B, but similar story. So this is saying that essentially if A to the power sends X to Y, then log base A will send Y back to X. And this double arrow is great because it works both ways. It also says, and that's saying that inverses work both ways. So if log sends Y to X, A to the power sends X back to Y. And the other thing you're going to be doing, which is kind of say more using the rules and not say if you don't understand this inverse function business, are you completely lost? No, you're not. If you have an exponential equation, you can rewrite it as a log equation. And if you have a log equation, you can rewrite it as an exponential equation. And I'm probably going to do that quite a bit. So this is saying, so say take P, apply the b to the power function, and you get say n, which is b to the power of p. So this is the b to the power function. And then if you apply the log base b function, so you start at p, you do b to the power, you end up at n, and then if you do log, it's the inverse, it'll bring it back to p. Be careful what I write here now. That actually shouldn't be. Change this picture a little bit. So you go back to p. So I want this to be just log base b, I want this to be b to the power. B to the power. Okay, I'm just drawing a little box there. Similarly, if you start at n, and you want to do log base b, and you get to p, and then you do b to the power, you will go back to n. So do log power, back to where you started. P, do power, then log, back to where you started. And there's a thing here that logs are powers. So if you like say if, how does that make sense now? So yeah, so if you do say 2 to the power of 3, and so that's 2 to the power, and then do log base 2, it's the inverse of it. You go back to 3, and this is what I mean by, this is a log, and it is a power. Okay. So this is kind of how you can remember this, but you don't have to remember it because here it is. Right. So let's that's our definition of log. We've used different bases. I think what we'll do here is we'll pause and do more examples in the next thing.